next speaker we have is Charles Shiflett. Charles is a senior software engineer with IBM Aspera Solutions. So I loved his description. He describes himself, I'm sure in common with many people here, as having a slight obsession with packet I/O. So I just like the description. So he's going to talk about how Aspera's fast, adaptive, and secure protocol uses standard hardware and DPDK to achieve 80 gigabit per second line rate. Over to you, Charles.
Hey, good morning, everyone. Did you feel the earthquake this morning? It was pretty exciting. So it's sort of like a welcome to San Francisco for everyone outside of this place. So anyway, I wanted to start off just by saying, please, anywhere in my presentation, if you have any questions, please stop me. What I am is a senior software engineer at Aspera. We are a recent acquisition of IBM, so I just wanted to do a quick shout out to the fellow IBMers here and just to say hi. And so what I'm going to do is I'm going to try to talk about the software that I've been writing, which is about an 80 gigabit per second network stack along with the storage I/O to make that go fast. And I'd like to frame that in the context of DPDK, which is this API that sort of allows you to do this high performance I/O, orders of magnitude speed improvement compared to what we were able to do before. So I'll go into why that is and how it helped us overcome what our slowdowns were, so to speak. So I'll go ahead and start with why are we using DPDK. I think you guys probably already know this, but what I think is really cool about it is it's this lightweight API around network and acceleration cards. And it's a vendor-neutral format, so we're starting to see support from like Mellanox, their 100 gigabit cards, which I'm very excited to work with. IBM recently added support for DPDK, so I think they may be the first non-Intel processor that you can use within this framework. And what does that allow you to do? It's this rapid iteration, at least for us, on high-performance transport protocols. So prior to DPDK, if you wanted high performance, it had to be in a kernel. And once you're in a kernel, not only does it take longer to develop that code, but you don't actually want your code to be in the kernel because you're dealing with user-land applications. So as you move along in terms of what DPDK provides, you also get this set of performance best practices. So how do you get timing information from the core that you're on in a quick way as possible? How do you do locking? How do you do memory alignment? How do you do synchronization? And then on top of that is this sort of how do we avoid libc and all that goes along with that, as once you've taken care of memory alignment and synchronization, what's the next thing that slows you down? Well, libc and some of that overhead. It's a NUMA-aware solution, and most importantly, it's a framework for high-performance user-land direct I/O. And that is probably going to be repeated about 3 times in this presentation, because that's really where we get the speed up. And so the goal of the software that I wrote was to have a transfer solution that really brought data closer to the people that were using it. And this is really sort of for us, the next generation. Aspera as a company has been very successful in sort of the media and entertainment industry. So whereas before content used to be sent over things like satellites, we're able to give people that same solution where they send it over regular IP packets. This next generation goal, it is quite frankly to just utilize existing hardware in a way that we're getting close to 100% utilization. So what does that mean? We're going to use your PCI Express in as much so as is possible. We're going to solve the storage bottleneck that exists, and I'll go ahead and talk some more about what that storage bottleneck is. We solve the network bottleneck, and so with DPDK, not only do we solve it from talking to a single network card, but we're able to aggregate multiple network cards together to give you pretty much throughput limited solely by the PCI Express bus. We're able to also provide a secure transport solution, and we do that by taking advantage of the hardware AES support on the Intel microprocessor. So what does that all mean? It just means significantly reduced time getting the data from wherever it is onto your target CPU anywhere in the world. So how do we show this? Well, we came up with a demo, and we had worked in conjunction with Intel on this, where we were able to use 5 Intel NVMe drives, and then we connect that to a dual socket Intel Xeon Haswell system, along with 2 40 gigabit network cards. And that is going to be our test setup that we talk about throughout this presentation. This solution, we demoed it in 3 configurations across the LAN, in a memory-to-memory configuration, and then finally in a WAN environment between New Orleans and Chicago and back. So I think it's very exciting. It fits in with the goals of Aspera, which is to build the fastest network protocols that take data anywhere in the world at maximum speed. So what does that mean? It really sounds kind of cheesy, but to just give you a little background on what Aspera is, what the problem is we're trying to solve. If you looked at normal network technologies, for instance, TCP, it's limited by round-trip time and packet loss, and that's sort of a function of the sliding window, the window size that you have, and how it does the acknowledgement. So as your round-trip time increases or your packet loss increases, your maximum throughput is going to decrease. There's a number of solutions to try to get around that bottleneck. It's sort of beyond the scope to talk about all the alternative solutions. The main points to talk about with our technology is that